In this video tutorial, we're going to look at natural logarithmic functions, and that has to deal with the natural base e. So we have to start off with recalling the compound interest formula, which we have a equals p times 1 plus r over n to the nt. And when we look at that, a is the final amount, p is the principal, so what you start with, r is the annual interest, n is the number of times the interest is compounded per year, and t is the time in years. Suppose that $1 is invested at 100% interest, so r equals 1, compounded n times for 1 year as represented by the function. So let's take a look at our original function would be, this is what we're going to start with, and then we're going to plug in our values. So a is the final amount. Our principal we invested was $1. Our interest rate is 1 plus, our rate is 100%, which is 1 is decimal, so 1 over m, raised to the nt, but we said t was 1, so n times 1. So if we take this formula and put it into the calculator and use x for our n, then what we will notice is that it will be approaching a particular value. Kind of looks like it would go on forever, but it actually approaches one particular value. So as n gets very large, interest is continuously compounded. Because n just keeps getting bigger and bigger and bigger and bigger and bigger and bigger and bigger. So if we examine the graph of this function, a equals 1 times 1 plus 1 over n to the n, what we'll notice is anything to the 0 power is 1, and 1 times 1 is 1. So we're going to have this point right here at 0, 1. And then what's going to happen is right about 2.7, our graph is going to taper off. So we're going to come up, and it's just going to come right up and just hug along this line at y equals 2.71 and on and on. So that is where this value continues to be. No matter how big our number for n gets, it approaches 2.7. So what they did in the math community and said, okay, well, you know what, that approaches 2.1 or 2.7, we're going to call that thing e. And so now we have a natural log where when we continuously compound something, we know it gets to be 2.7, and so we're just going to use e instead. If we look at the exponential for that, we have f of x equals e to the x. So if we look at that graph, if we plug in 0 for the exponent, e to the 0 is 1, so we still have that point here at 1. And then at 1, it's 2.7, so we go up here at 2.7. And if we increase the exponents, again, we know that with exponential, it's going to hug along this curve and then go up. So in our equation on the left for a equals 1 times 1 plus 1 over n to the end, we know that the function has a horizontal asymptote because it goes up to 2.7, but it never really gets up to that 2.718 number. So we have a horizontal asymptote. as n becomes, whoops, infinitely large, the value of the function approaches approximately 2.718, oops, 28, no. This number is called E. So like, let's say pi, and the constant E is an irrational number. It does not repeat. So exponential functions with E as a base have the same properties as the functions you have studied. The graph of f of x equal e to the x is like other graphs of exponential functions, such as f of x equals 3 to the x. The domain of f of x equals e to the x is all real numbers, and the range is y greater than 0, which is what you found for the other exponentials. A logarithm with a base e is called a natural logarithm and is abbreviated with ln. Rather than as, let's see, log base e of x, we're going to write the natural log of x. So log e is actually ln. So natural logarithms have the same properties as base 10 and logarithms with other bases. The natural logarithmic function f of x equals a natural log of x is the inverse of the natural exponential function f of x equals e to the x. Remember that inverse functions reflect over the line y equals x. So the domain of f of x for the natural log of x is x greater than 0, and the range of the natural log of x is all real numbers. So what you should notice that this is the reverse of what happens with an exponential. An exponential function says all real numbers for the domain, and y is greater than 0, and when you flip it over the y equals x axis, then it becomes the x is greater than 0, because now we have this asymptote running here instead, where we have our curve. And then we can pick any y value that we want, because it goes on forever this way and on forever this way. It just keeps going up. So let's take a look at some examples. So all of the properties of logarithms also apply to natural logarithms. So guess what? Natural log of e is really log base e of e, which means this cancels out. And the answer is 0.15t. Go ahead and pause and try number 2. There are a couple of ways that we can look at this problem. What I'm going to do is I'm going to look at natural log of e. That cancels out. So this becomes 3x minus 2 because I would normally bring down the exponent. And then minus, well, natural log of e cancels out. The x plus 5 would have come down as the power property in the front, so x plus 5, and then I would combine like terms. So 3x minus x is 2x. Negative 2 minus 5 is negative 7. Go ahead and try number 3 and pause the video. In this case, we have e, and then it's 3 times the natural log of x plus 1. So let's just rewrite that because we can't really take e to the third right this second. We'll just move that over and go by the properties of power. So ln of x plus 1 cubed, and then e to the ln cancels out, and we end up with x plus 1 cubed. Go ahead and do number 4, number 5, and number 6 for homework. Number 7, we're going to work with that just like we did when we had logs equal to logs. So to cancel out a natural log, I will exponentiate. So e to the ln negative 3m plus 8. And on the other side of the equal sign is e to the ln of 4 minus 5m. So e to the ln, what is that really? E to the natural log, so we can cancel that out. And we get negative 3m plus 8. And e to the natural log cancels out, and we get 4 minus 5m. And then we can solve. So let's add 5m, and we get 2m plus 8 equals 4. Subtract 8, and we have 2m equals negative 4, and we divide by 2, and m equals negative 2. Go ahead, pause the video, and try number 8. Just like we did in number 7, we're going to exponentiate e to the natural log, e to the natural log and e cancel out, so we have 2a minus 9 equals a plus 1. Subtract a from both sides, I get a minus 9 equals 1. Add 9, and we have a equals 10. Go ahead and do number 9 as homework.